This is my project on cancer in dogs. So the background, over 6 million dogs die of cancer every year, and approximately 1 in 2 dogs will develop cancer sometime in their lives. Due to shorter lifespans and biological similarity to humans, dogs can be used to study human cancers as well, and understanding canine cancers can help us prevent their deaths and understand human cancers better. Cancers can be treatable or curable if found early enough in dogs, and finding predictive factors for cancers will allow for more frequent screenings in at-risk populations. Finding mortality factors for cancers will allow for more accurate and targeted treatment plans. So my two statistical questions are: do purebred dogs have a higher chance or have a higher cancer diagnosis rate than mixed breed dogs? And is there a correlation between dog breed size and cancer mortality rate? My population for my first inference is all purebred and all mixed breed dogs, and my sample will be the 1.61 million insured dogs in the nationwide pet insurance database, with approximately 966,000 purebred dogs and 644,000 mixed breed dogs. The nationwide pet insurance database contains all its insured pets, as well as the number of them that have received cancer claims, 2.5% for purebred dogs and 1.3% for mixed breed dogs. I will be performing a two-proportion z-test hypothesis test for this inference. So we'll say P1 is the true proportion of purebred dogs with cancer claims, and P2 is the true proportion of mixed breed dogs with cancer claims. The null hypothesis will be that P1 and P2 are equal, and the alternative hypothesis will be that P1 is greater than P2. Alpha will be 0.05. Here's the data table. My assumptions and conditions: the two samples, purebred and mixed breed dogs, are independent of each other, and the samples are both representative of their overall populations. There are at least 10 expected successes and failures in each sample group. 966,000 times 0.025 is equal to 24,150. 966,000 times 1 minus 0.025 is equal to 941,850. 644,000 times 0.013 equals 8,372, and 644,000 times 1 minus 0.013 equals 635,628, all of which are, of course, greater than 10. So P hat 1 equals 0.025, P hat 2 equals 0.013, and our pool proportion is going to be equal to 0.0202. Calculating our standard error will give us 0.0006 or so. And then getting our z-statistic will give us 18.5790, which gives us a p-value of approximately 0, which is, of course, less than our alpha value of 0.05. So our conclusion for the first inference is that because the p-value is much less than the alpha, we can reject the null hypothesis. There is significant statistical evidence that purebred dogs are more likely to be diagnosed with cancer than mixed breed dogs. This means that purebred dogs are at a significantly higher rate of developing cancers and should be ideally screened for cancers at a higher rate than mixed breed dogs in order to lower the risk of mortality. So our population for the second statistical inference question is going to be all dog breeds worldwide and their associated average weight and cancer mortality rates. My sample will be a data set of 10 common dog breeds with reported average adult weights and cancer mortality rates sourced from several studies and databases. This data set includes breeds ranging from small, like Chihuahuas, to large, like Great Danes, with corresponding cancer mortality rates. I will be performing a linear regression analysis to investigate whether there is a significant statistical relationship between a dog breed's average weight and its cancer mortality rate, as well as constructing a confidence interval for the slope of the regression line to determine if a relationship exists. So the line of best fit is going to be 3.075 plus 0.3415x. And we'll say beta is the true average change in cancer mortality rate as a percent for a 1 unit change in average breed weight. We're going to be taking a 95% confidence interval. Our assumptions and conditions are that the scatter plot appears linear, there's no pattern in the residuals, The error variability appears to be constant across all x values, and errors are normally distributed. So n equals 10, our degrees of freedom is going to be 10 minus 2 equals 8. Our t-critical value is going to be 2.306. B is 0.3145 from the line of best fit earlier, and this deviation of B is going to be approximately 0.0273. So now just calculating the confidence interval, we're going to end up with 0.2515 to 0.3775. This means that we can say with 95% confidence that the true average change in cancer mortality rate as a percent for a 1-unit change in average breed weight lies within the interval of 0.2515 and 0.3775, meaning that we can say with 95% confidence that there is a meaningful statistical relationship between average dog breed size and cancer mortality rate. This means that heavier dog breeds are at a higher risk of dying from cancer than lighter dog breeds, and treatment plans should be created with this in mind. So for the reflection, based on the conclusions from these two tests, we can conclude that higher weight dog breeds are more prone to cancer mortalities and that purebred dogs are more prone to cancer diagnoses. Some ideas for further study could include rates by age, specific breed, or types of diet. And here is my work.